What I'm going to talk today is going to be really in a three. The talk will be divided in three parts, and talk is really based on the work with Istokozo and Gordon Goliath. Some of this already published, some of this was not published, but I really was hoping to talk about and get maybe what's collaboration. And for you interested, Istok has developed these great programs that all this hard work in terms of coding and programming, and I always bug him for another option. But if you're interested, just let us know, and we're happy to share with you. So let me just start basically provide the conceptual framework that I'm sure that this is the type of framework that all of you actually have thought of over the years, and probably have a different ideas one way or another how to go about this. But in general, as we all kind of with the rise of evidence-based medicine, we all agree that our inferences and our decisions should be based on best evidence. Well, best evidence, best empirical evidence, hopefully on totality on empirical evidence, particular topic, is often really expressed in terms of systematic review meta-analysis these days. But even if it's not expressed that way, best empirical evidence typically is based on some sort of the group observation on the group averages, and as you know, there's no such a thing as an average patient. There's no average individual. So it is always kind of a little interesting that this is the best we have, but at the same time, it's really applicable to some non-existing patients, basically. And but at the same time, the physicians and patients, they really need we would like to actually have the evidence or treatment effect that's directly applicable to us, to individuals who actually eventually are going to be really be on receiving end of any health intervention. And so, as you will know, the group effect sizes do differ from individual effect sizes. There is a huge heterogeneity in this treatment effect, and this heterogeneity of treatment effect is a central practice to popular, personalized, or precision medicine. And obviously, some patients are at higher risk to begin with, others at lower risk, and so in the last decade or even people increasingly trying to develop predictive model in order to tailor interventions to particular individualized risks. But the issue, the problem with predictive model is that they pretty can be accurate to individualized prediction of outcome, but they do not take consequences into account. Therefore, they really are not prediction models. Typically, how most of them develop, they really do. They don't have inherent clinical utility. To have that clinical utility, you have to take the consequences into account. And that can be done really within the framework of decision analysis. So idea is really you have to really integrate the predictive models within the framework of decision analysis. And one of these decision analytical framework that's been developed called decision curve analysis. And most recently, we built on that and we call it the generalized decision curve analysis. Idea is really that personalization is obtained by actually determining, calculating threshold above people with particular risk should receive the treatment. And so just to kind of put this in a concrete example, what I'm trying to say, so you have average and this particular model, the data from particular model that we were actually developing in terms of prediction venous thromboembolism in patients with cancer. And if you take on average in this particular population, I think it was about 400 or so patients, about 13% of patients develop clot. But obviously, some people actually have a higher risk to develop clot versus others. And therefore, the risk predictive model was developed. And basically, in this particular case, this is you're talking about so-called low risk, medium risk, or high risk, here shown as 0, 1, or 2. And as you can see here, the risk can be as low as 3% to as high as 32%. But the problem here, and so when I talking about individual risk, I should really say it is really misleading that we can talk about truly individualized risk. As you can see here, for example, people are here the risk to developing VT of 32%. They are all in this group, but some patients will develop this clot, other patients will not develop clot. And in other words, we can be pretty much good about predicting risk or outcomes at the group level, but the risk at the individual level is actually is the fate or outcome individual is really unknowable, it's a real field of precision medicine. I have heard and read interviews with the major the companies of major pharmaceutical companies that say, hey, we should dispense with this large randomized trial. We will go identify a small group of the patients, and we want to develop the precision medicine that is actually targeting according to the risk. The problem with that, there's a really huge heterogeneity when you think about all of these potential combination of genome or disease, social and environmental factors. We actually need to have a much larger trials instead of smaller to identify those risks that we can call precision medicine. I think John and I actually made this point a few years ago, actually, in this commentary we wrote about that. So the question then really, how do we make those rational, again, personalized decision with understanding that really truly personalized decisions are theoretically impossible? Well, obviously, so the key question is here that we have to move from evidence that exists on a probability continuum, risk exists on a probability continuum, and then link it to decision making. And so the key to all of this is that our decisions are categorical. We make them in some threshold, and some risk threshold, probability threshold. And all idea here, you're going to make actually personalized decision that the people who actually with the risk threshold above certain probability where benefit outweigh risk, harms should get treatment, otherwise wouldn't get. Interestingly, we recently made a point that that this probably represent one way to pragmatically even address that ancient Sorites paradox. I hope I pronounced Sorites correctly here, but some of you, it's. I'm always amazed how ancient Greeks thought about concepts that never really, they're still with us to this date. You would think we'd have solved them by now. But anyhow, Sorgy is what I understand in Greek means a heap, and the whole issue is if we start removing a grain of each grain from the heap one by one, at some point heap stopped being heap, and that's the question really. And when you categorize something being heap versus grain, when you categorize probability risk high to act versus not to act. Again, this is going to be related to this threshold model. So just to kind of really just give some explanation in terms of cartoon here. So we develop predictive model. Usually in this predictive model business, we have a bunch of statistics to tell us if our model is accurate in terms of predicting outcomes or whatever clinical event of interest. We usually use some sort of a bunch of discrimination statistics, like whether area under curve, C statistics is a lot, sufficiently large, like greater than 0.7, often people say, or does it calibrate well, whether whether what we observed is what we expected to observe. So that's kind of first step into development. But and again, as I was saying, risk as a group phenomena is pretty knowable at the level of as a population measure. It can be knowable, and this is an argument here, at a smaller group as much, but at individual level, a truly individual remains unknowable, because patients will develop or will not develop the outcome of interest. That's how frequent this probability at least works. But the question then becomes how high that risk ought to be before we should act. And the argument is here, well, it can be, it should be as depending on a function of the consequences of treatments, benefit and harms, and patients' value and preferences. And here you can see here in this cartoon, you have actually this threshold that's independent of risk prediction. And if you are then above this particular, if you are above this particular threshold, you should administer treatment. If you are below, you shouldn't. So that's kind of what we think by this individualized decision making. Because heart of all of this is a threshold model, let me spend a couple of minutes to explain how this threshold works. There are many variations of threshold model. This is probably, the original model was published almost 50 years ago now, and it's probably one of the major advancements in the history of clinical decision making. And again, and this is a simple model that's been developed from many different theoretical point of views. We work a lot on regret theory, but mostly is being used within a concept of within the framework of expected utility theory. So in this little, this simple model, basically, we have decision to make. That's only where we control the process. You make decision, we can treat patients, decide not to treat patient. And then after that, things happen as a function of chance. Patient will have disease or outcome of interest or not have disease. If you treat somebody with disease, they will experience certain outcomes. We usually call them utilities. Or if that patient has the disease, or if patient doesn't have disease, outcome will be different if they're treated. And the same story down if you don't treat it. If you don't treat it, patient will have disease, you'll have certain utilities. If you don't treat it, patient has disease, you have a certain utilities. Important point here, trick here, if you want, which original paper is that we define net benefit as a difference in outcomes or utilities from of those patients who were treated and have outcome versus those patients who were treated, who were not treated and had outcome. And the same, we define harms as a difference in outcome of those patients who didn't have outcome and they were not treated versus those who didn't have outcome were treated. I hope this makes sense. I know I'm going fast. I know many of this is already very familiar to you, but I think it's important to kind of mention this. And your question then becomes, at which probability, at which threshold, there must be some threshold at which probability of disease in this particular case is equal between treating versus not treating. And so we are now interested in finding that threshold, the probability of disease. And if you solve this equation here, this is what you get. And that is the classic threshold equation where benefit and harms are expressed in what we call it in a holistic or a global terms. But what we are arguing, hey, look, we started all this evidence-based medicine in order to be very specific and explicit about outcomes. Yes, so with subjective values of benefit harms, could be important, but we need really to decompose the benefit and harms in whatever type of metrics we think is appropriate. And here and there's different ways how you do that, but here I'm just going to talk about two ones, and we decompose this benefit and harms in terms of harms of treatment expressed in terms of absolute absolute harms, relative risk of reduction. You can do other metrics, and morbidity or mortality of a particular condition that you're dealing with. Or if you're dealing with the composite outcomes, you get actually very nice formula. You draw M is equal 1, and you get this formula basically for the threshold. So you can see here immediately how threshold function, how threshold solution is different depending on the metrics you used, and that will become relevant in the rest of the talk. So again, if you solve that equation I showed, and then you graph it, as you can see here, probability is a function of benefit and harms, the high benefit harms ratio, the low probability at which we act. In this particular example, I forgot a while ago which was example, but anyhow, benefit and harms is equal to 3.5 and converts in probability of threshold 21%, which means that if probability of disease, and this is in the brown, could be outcome is above 21%, you should treat. If it's below, you shouldn't treat. And idea is here that this is where a risk prediction model works. You want to know if your predictive risk is above thresholds or below the thresholds, and that's really what the decision curve analysis is all about. So basically, then the issue really becomes from technical point of view. Let's address generic question, and the generic question is whether we're dealing when you see the patients at bedside, or or in general, maybe in population science type of things, you're really facing two dilemmas. There are three options. Hey, should I do default? I shouldn't do nothing. People like this, I shouldn't do anything. Just that means treat none. Or should I? Or I face another dilemma. Okay, hey, look, if people like this come to me, everybody should be treated. So that's a strategy, treat all. Or I should say, hey, how about I use predictive model? And if predictive model is above certain threshold, I should treat. Is below threshold, I shouldn't treat. And that's actually basically this particular model, which is depicting. And the way actually it works, again, I showed you how in this decision curve analysis, basically you repeat this threshold over entire range of threshold. The threshold go from 0 to 100%. And basically you select the threshold, which is again, whatever however you calculate the threshold. You then select, if you are above that threshold, you define it as a positive, or higher the threshold, the risk free. You calculate the net benefit, and net benefit is calculated in a way that that it's a difference between expected utility of that particular branch where you use the model versus expected utility of that branch of no treatment. And that's formally you got it. That's original decision curve analysis that Vickers and colleague developed. We argued, look, you gotta really replace those global benefit harms with those specific ones, and then we get this particular formula. And basically what you then do, you just repeat this analysis over time in standard DCA or threshold in all generalized over relative patient relative values. And just to briefly to explain, again, explains the difference. In standard decision curve analysis, benefit and harms are implicit holistics. They're not explicitly expressed. They also actually used they used what we term scale net benefit, meaning they actually compare everything against the fixed value at 1. That creates some problem for evaluation of multiple treatment effect. You can't do it actually. You can't evaluate within decision curve analysis, standard decision, multiple treatments. While within our generalized decision curve analysis, you can do that. And the reason is basically we express a net benefit without scaling. Again, I hope I'm not complicating things too much, but Either way, you're getting some different results, and basically you express data overall probabilities of your risk prediction model. Again, the main difference is here that we explicitly model treatment effect using evidence-based measures like a relative risk reduction, HARS, and morbidity or mortality treatment, relative values, telling if relative value is 1, the patient doesn't really, is indifferent between benefit and harms. If relative value is less than 1, patient values burden of disease more than burden of harms, and other way around. If relative value is greater than 1, they value burden of harms more than disease. I forgot to explain it earlier. And so basically, there are really 3 types of decision curve analysis published out there. This would be standard DCA. You express net benefit versus threshold model, and then you express those 3 strategies I mentioned. One is treat none, which by definition is actually set at 0. Another is treat all, and this would be blue curve that happened here. And third strategy is, okay, use the model to drive your decision. So again, higher net benefits, the better strategy is. We can express the same things using this unscaled net benefits, where we don't fix everything to 1. And here in this particular example, which I'm going to really further detail in a second, we compared Framingham risk assessment model and 3 statins for primary prevention of heart disease. We just had those data and we played with those. And so you can express net benefit this way. We didn't really think that particularly informative, and so we decided to express net benefit versus relative value, or patient value and preferences. And so you can see here at RB1, with which would be typically where clinical trial would be, a results clinical trial, for example, meta-analysis we reported, where patient equally values benefit versus harms. You can see here net benefit for, I think in this case, pravastatin actually was higher than a net benefit of atorvastatin, and basically much higher the rosuvastatin. So you can see here that in this particular example, you can compare the effect of all 3 treatments, basically to telling you should I actually use model and act according to model, or should I actually treat everyone with the statin in this case, or I shouldn't treat anyone with statin case. I hope actually I'm coming across. If not, please feel free to interrupt. But here's a really example I'm really trying to illustrate. So in decision curve analysis, we are linking frequentist with decision statistics. Frequentist really refers only to input data. It comes from, in this particular case, network meta-analysis. Using this data to run this generalized decision curve analysis. And here, in this particular case, I think we use composite outcomes. And when we use a composite outcome, again, we're comparing several strategies. So again, one strategy, should I use statins in everyone? Or should I use pravastatin, atorvastatin, or rosuvastatin on everyone? Or should I actually use the model, Framingham risk model, and then if it's above certain threshold, I should treat. If it's below certain threshold, I shouldn't treat. For decision curve analysis right now is kind of telling you, okay, over all probabilities, and for RB1, we're interested, what's the best strategy? And here, using Framingham risk model, informing use atorvastatin by Framingham risk model seems to be best strategy. Now, that's for all possible probabilities that you can get. What actually happened? Oh, I forgot to say that. So this is a really important point. I already mentioned that that input is based on frequency statistics. Outputs are based on this net benefit, which is a decision analytical construct. And I guess you guys probably know this, but a lot of people are still surprised about this. According to classical statistical decision theory, magnitude of differences is completely irrelevant. The classical rules of statistical inference do not apply to analytical modeling. We don't really, decision analytical modeling, we don't really care about the confidence intervals or statistical significance. In other words, when choosing among different options, the most rational choice, according to decision analysis, they use net benefits with the highest expected utility, regardless is it the small or big, whatever the small difference, as long as the net benefits are highest, that's the one that should choose. Statistical significance is only important in terms of in relation to model inputs, but I believe that input data actually are we can be confident in input data or not, but they don't have any relevance in terms of our actually conclusions. Obviously, you can use a different assumption for those inputs in order to assess the stability of your conclusion. But a very important point is that statistical inference in terms of classical frequency statistics is irrelevant when it comes to inferences in decision analytical framework. Okay, so I showed you results when you take the model over all probabilities. In those cases will be Framingham risk models. But we know that that's, you know, some risk factors, some people, those probabilities still sort of average probabilities. So some people really can be categorized in much lower risk group versus other. For example, American College of Cardiology, American Heart Association recommends that people should be treated with the statins if their risk of heart disease greater than 7.5% over 10 years. I never figured out how they actually calculated that, but nevertheless, that's what they claim. So, okay, then what I did here is basically said, okay, let's just see how this decision curve analysis works in a low risk versus borderline risk versus intermediate risk versus this high risk as defined by American Heart Association. And what actually you see here, basically, again, we are interested in RV1 because that's how the trials were reported. But for the low risk, actually, very low risk, pravastatin is the best. And for borderline risk, I think pravastatin is the best. Again, I shouldn't say pravastatin best. The best strategy is use the model to inform whether you should use pravastatin. Again, for borderline as well. For intermediate, however, things changing. For intermediate risk greater than 7.5%, less than 20%, using atorvastatin becomes better strategy, and almost actually use atorvastatin without really thinking about anything else, which remains also for high risk strategy. This can be better visualized this way. So you have net benefits here on y-axis, and then you have a low risk. Then you have a low risk group here, borderline risk here, intermediate according to American Heart Association. And you can see here, you can actually then find that don't do anything if your probability of heart disease less than 0.15%. Pravastatin is best between 1.5 to 8.3%. Atorvastatin would be best for the rest of it. So that's basically how we get to this so-called individualized decision making. Okay, I think I took longer than I expected on the first part of the talk. So I'm not going to ask you if you have any question, because Max warned me that that he's going to interrupt me about 10 minutes from now. So I better to finish the rest part of talk, the rest of the talks. Okay, so this was, hopefully you got the message, the first part of talk. I meant to stop it and have some discussion. Turned out I didn't really time it well. For what I showed you before, basically, you needed individual patient data. But the problem is individual patient data, it's very difficult to get hold of them. Regardless of all of our publishing, hey, we need to share the data. People don't share the data. It's very difficult to get hold of this data. So a while ago, we did Monte Carlo modeling and showed that you actually can basically, you can actually simulate same predictive model using Monte Carlo models. You know, that didn't get much notice, so we thought, let's just kind of extend those observations. And so the bottom line is here, because of the record of the time, I'll go very quickly. It is possible to model that decision curve analysis, and I'll show you how accurately, if you actually if investigators would just report mean and standard deviation from their predictive models. And basically, the theory behind that, if you use those standard mean standard deviation, mean standard deviation from predictive model, and express them in a better distribution, you can enable that that outcome will remain between 0 and to 1, and regardless what's otherwise underlying regression model that was used in the developing predictive model, you actually still getting results as you would get them in individual patient data. What's really interesting here, that you don't need data. Originally, we simulated outcomes. You really don't need, you don't need to simulate outcomes in order to generate those reliable aggregate data. Let me show you why. So typically this would be, you have some people with a patient with outcome, you develop models, you assess, calibration, discrimination, and then the main hypothesis here is for well-calibrated predictive models. If you are the sum of all these predictive models is above the threshold, will actually have to be will have to be equal to some of the true event or false event, because you already know by definition where your threshold is, and as you create a better probability density function, you basically can really just count all of this number of events there. And if they are truly above a threshold, then we define this as a true positive, sum of all pi's, basically p the probabilities, or 1 minus that would be false positive, and basically then from this you can get those probabilities and run decision curve analysis. And then we did a bunch of the analysis, simulation to show, whether this matters, how you develop the original model, when you convert beta regression, whether it's a logistics or uniform or viable. Pretty much the differences between minimum and maximum is pretty much negligible. So we kind of concluded actually this seems to be working. And then when you compare the individual patient data that we had versus aggregate data, here's, for example, when you have a lot for Framingham, you don't even see the difference between it's almost overlapping individual patient data versus aggregate, whether we're dealing logistic curve or we're using Cox. Same here, something called support model for predicting actually survival and end of life setting. But when both Framingham and support, they were They were really well-developed model. They will, you know, they have good collaboration, good discrimination. When you have actually smaller number of events and smaller sample size, there is some, as you can see here, there is some not complete overlap between model developed on individual patient data and aggregate data, but nothing in terms of affecting your decisions. When you have the really small numbers, then things actually get a little bit more dicey here. So we kind of concluded if you really have a well-calibrated model, meaning really just a large sample size enough, then using standard, just a mean and standard deviation, you can actually run this analysis. And again, you know, here's a basically idea. You're showing how different. There was almost no difference between and whether you're using individual data or aggregate data. Aggregate data just allow you to kind of extrapolate results, you know, further from the data you have. Okay, so these two things are already published and or are in process of in the press. But what I'm arguing here, look, we currently doing all of this meta-analysis or aggregation or summary using an inference. I've never seen a situation that we are aggregating data for clinical utility. You pretty much, you know, aggregate data level of evidence, sometimes diagnostic test. And so I'm asking, hey, maybe we should start to aggregate data at the level of clinical utility. Kind of we started thinking about this. If any of you is interested, please contact me. I love to develop some collaboration and see actually if we can move this forward. But the idea is here. Look, you have a standard, the mean and standard deviation, and then you run. This could be from one model, or could be for a bunch of other the models. You don't want to. You basically then just aggregate them. And in this particular case, for example, we run beta distribution 20 times, and then for 5 different models, and we just aggregate them, and we get kind of this meta-analysis of this clinical utility data, so to speak. And you can do for the same for the gDCA. And we develop the software, and you know, and then you can use it for predictive models. You can do for multiple models. So basically, so idea is how to move this forward in kind of a more definitive way. Again, idea is to aggregate clinical utilities rather than inferences. And so here's my conclusion. So the best evidence obtained in the trials or meta-analysis of trials refers to treatment effect for the average patient. Clinician patients, however, are interested in personalized treatment, so we would like to tailor treatment to what patient individual risk characteristics. Generalized decision curve analysis allows selecting personalized treatment according to individual risk characteristics. If individual patient data not available, we can obtain similar results or almost identical results using summary estimates from each predictive models. That can then facilitate then meta-analysis for clinical utilities. And we think that that if these things are started using more widely, this aggregate data, similar to what happened with the Cochrane collaboration revolution, basically people will start doing more systematic review and meta-analysis of predictive models or clinical utility models. So we think standards for reporting diagnostic test and predictive models should include the mean and standard deviation of each of predictive models as mandatory reporting items. I think I finished 12:45. Rushing a little bit to heed Mac's warning, but anyhow, maybe we can open some discussion. Thank you.